Okay, week 5, so lecture on moving from the logical to the physical design. It's hopefully a relatively short lecture compared with some of the others, so hopefully we'll be done shortly after an hour. Then I will, after the break, or we might have a break before the end of this lecture, depending on how much I go on, want to run through the assignment, just briefly talk about the assignment, what you need to do for 20 minutes, 15 minutes, 20 minutes. And there is one final thing that we need to do. When we've finished all that, I shall leave you with a couple of forms because it's early module feedback week. I don't know if you've done this with Nigel this morning. So is there a class representative? I haven't heard of one being notified. No, doesn't matter. Basically, if somebody can take the lead, actually write it down. So very simple. You just list some good things about the module, some things that might be improved, and any other comments you like. Totally anonymous. Hand it to me at the practical. Yeah. I won't know who's made the comments. I might know who's writing it. By the way, anyway, I will leave you to finish that. Okay, so physical design. So basically 2 sections. A little bit about moving from a logical design to a physical design, and then the process of normalization, which is part of the physical design process. Just to remind ourselves where we were. So we're looking, the waterfall development model is the entire process from the conception of an item of software, an software application, through to its use and potential review and new developments. So last week we saw the idea of the conceptual model, the overview of what this system is going to do and what the various main components it connects. We then through the logical part of database design, ER diagram, basically your ER diagrams. Talking about ER diagrams, so we had a little in-class exercise last week that went okay. I mean, personally, I would have liked half the day to do it, or at least, if not longer. I thought there was a lot more that we could have done on that. So far, I've had to talk to 2 people who've shown me their ER diagrams. They either extended from last week or developed, and made some comments on them. I emailed one of them round to you. Keep them coming in, basically, and hopefully if you can see the comments I've made on other people's ER diagrams, you can take those comments and integrate it in your own, and maybe in a week's time we'll actually have a really good design, sort of almost crowdsourced, if we keep sort of considering each other's, the comments I make on people's design. I must say it's something that takes time and practice and thinking. Just because you can draw a box and a few lines that connects the box doesn't mean you've got it right, or that it's drawn correctly. So please do make the effort to try and spend some time drawing logical designs and trying to approach them, sort of take them apart, give them to your friend, or if you've got a friend, Do you draw one, give it to your convert, see if they can understand it and see if they can take it apart and say, well, what do you mean here? What happens here? What is the exact relationship between these 2 entities? Anyway, so logical design. So today we're doing physical design, the process of implementing a logical design. Just remind ourselves what a logical design is. Fully specified in inverted commas. I'll come back to that at the end. Abstract representation of software system design, independent of any particular software. So we knew that last week. And the physical model that we're moving to is the logical model implemented in some specific software solution. So what do we need to do? How do we get there? Well, this is just a list of the sorts of things that need to be done. Entities and relationships are implemented as tables. So you have to take your entities and your relationships in your ER diagram, expand them up to tables, or blow them apart into tables, depending on which way you want to look at it. because an entity in an ER diagram or a relation, particularly relationships, but also some entities, in fact turn out to be implemented or need to be implemented as multiple tables. Now, there is a tendency, especially for small databases with not many tables, for tables to be equated to entities. So one entity equals one table, and all tables are entities. So if you went to your physical model, all the tables in your physical design would map to one entity in your ER diagram. And there's nothing wrong with that, per se, but the whole point of ER modeling was to provide an overview, to stand back from the minutiae of the problem, the individual tables, how the individual tables are implemented, and to look at the problem as a whole, and to have a sort of iterative design process whereby you slowly develop your understanding of the entities that are required for the system and how they relate to each other. Okay, so you may end up thinking, well, isn't an entity relationship diagram just the same as a physical design of tables? No, it's not, but it can be with simple with simple data models. To a certain extent, it's difficult to teach some of these things, I think, because most of the time as students, you've got a short period of time to understand these things, and in small, simplistic systems, all the problems don't emerge. It's only in larger systems, more complex systems, that the real benefits of ER modeling really come to the fore. Okay, so attributes and relationships implemented as tables. Entities and relationships. Attributes implemented as data types. So in an ER diagram, it's just a name, address, surname, first name, color. But you actually have to implement that in the physical design as an actual data type. I'm going to use an integer, a small integer or something like that. We need to implement domains on columns. Now, okay, domains aren't part of the ER diagram, but they're still something that needs to be implemented in the physical design. Tables are normalized. Now, I've been thinking about this over the last week, and there's quite a lot in common between normalization and drawing entity relationship diagrams. To a certain extent, if your entity relationship diagram maps pretty much onto your tables, so one entity, one table, then you've done the process of normalization, or a lot of the process of normalization, in designing your entity relationship diagram. However, if you've got your entity relationship diagram is more of one of these higher level views, then normalization is more understandable to separate normalization from the entity design. You need to instrain constraints on columns, things like primary keys, as well as topological constraints, so primary foreign key pairs, and any other topological constraints that might be implemented. If you don't know what a topological constraint is, don't worry about it. That's basically a spatial constraint, and we'll talk about that after the summer holidays, the enrichment week. I've got indexes built there, but I've actually taken, so last year I talked about indexes in this lecture, but I've taken it out this year, so just ignore number 6. We'll talk about indexes in a later lecture. Okay, so first things are, you've got choices about how you name things in your database. So first of all, they vary. The rules about what you can call things like tables and columns and domains in a relational database is going to vary by the database. They all have their slightly different rules. So for example, in Postgres, a table name can only be up to 63 characters long. I believe it can't start with a number as well. So that's just the rules of the Postgres database. So there may be particular rules for how you could, what you're capable of actually naming a table. Physically, the database management system constrains what you can name tables. Also columns, any other data object maybe has a similar types of constraints on them. So there are the rules that the system, the software imposes upon you, and then there are rules that you impose upon yourself because it's a good idea, so coding conventions. So things like, you know, to a certain extent these are hopefully totally self-evident, but we need to remind ourselves. So assigning meaningful names to tables and fields. Don't call it table 1, table 2, table 3, table 4, table 5, column 1, column 2, column 3. You'll soon get confused and lost. And anybody else looking at the database will not have a Scooby what you're doing. So, you know, use meaningful names. There's a general convention that table names and field names should generally be in the singular, not the plural. So river, a database of a table of rivers, or river data should be river, not rivers. You know, one is it saves one character. Every character that you don't have to type is improving your efficiency, as long as it's clear but what it means by not losing that. I failed on this. I mean, I hasten to add, throughout all the slides and all the practical materials, you will see me breaking these conventions all the time. Okay, and I apologize for that. One is I'm perhaps not the most careful and person in that respect. When it comes to science, what they say, what sort of science do you do? Well, I sort of take things, keep a spadeful of this, you know, into a bucket, stir it about with a stick and then see what it looks like, rather than going into a lab and weighing everything to minutity. I tend to be a sort of broad brush kind of person rather than specifics. But if I was involved in some large project that involved multiple people coding, I would try and follow convention and I would try and be better on convention. And when I go back next year or the year after and rewrite the entire practicals and things like that, so I will try and make things more consistent. To a certain extent, if it's just you doing a development, consistency is not that important. It will help you, but it won't be a disaster. When it starts to be really important is when you're working as a group and people are developing different parts of a software solution, and if you're not using similar naming conventions, then you're soon going to get yourself in a bit of a muddle. It's going to be more complicated, so do that. Okay, other things like consistent capitalizations of and use of underscores. Do I remind myself again? Never use a space, never use a parentheses, never use all these odd characters. If you want to separate words in a string, then you can use an underscore or you can use capitalization. So I think this came from the Postgres style manual. So table names, it suggested you use what's called Pascal case, capital P for the first word, capital for the second case. So they suggest using that Pascal case for table names. Camel case for column names. So camel case is where you start with a lower word. Your first word has a lower, starts with a lower case. Your second and subsequent words have a higher case. It's meant to look like a camel's hump. And function names generally have a underscore and all lower case. You know, and certainly in Postgres, as you know, as soon as you start using capitals, you have to start quoting things as well. So, but anyway, I think that's the recommended from the style guide for Postgres. Never use spaces, other characters, ever, 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 yeah. Right. So there are the constrictions about what the system does. I should have mentioned on that slide as well that if you're working within an organization, a large organization, there's often coding standards imposed by the organization. Be it government, be it IBM, be it whoever you're working for, they may have an in-house style. So be aware of that. If you're producing something for an employer, is there now an in-house style? And if there isn't one, maybe you should suggest that they adopt one, perhaps. Okay. Entities and attributes. Entities are converted into tables and attributes into fields. Defining tables and fields. Now, this, to a certain extent, this should also apply to the logical model and your entities and your attributes of your entities. So this is not exclusively perhaps relevant to the physical design. So what do you need to consider when defining tables in their fields? Well, obviously, if you've got existing data, you have to consider the structure of that existing data, and that's probably going to be your starting point. So, you know, what exists? But one has to be very careful about solely basing one's design decisions on what you have, what you're given, so to speak, because of that is a subset, almost unless it's a complete clean data set that's never going to be added to and it's static, the data that you're given may not capture all the entities and relationships that could exist in the domain. Okay? You've got a database of cars and nobody has ever, and it doesn't include a yellow car. Well, there are yellow cars out on there on the road, and if you implemented a domain of colours on your car colour field, and because yellow didn't appear in the list in your data set, you don't include it in your domain. Well, clearly that's going to, as soon as a yellow car comes along, you're in trouble. So think about the data itself that you've given, the existing data may not totally embody the problem. Quite often, new databases are built because something is going to happen, something new is happening. So there may be new data to come in that hasn't actually been collected yet, for example. So you have to consider what is going to be done. So what's the structure of the data that's going to be collected in the future? And to a certain extent, that's just, you know, that's existing data. You're saying, well, I know we're going to go out and collect this data and it will hopefully come back in this format. The reality is, from my experience, is that, you know, you've got a rough idea about what's going to be collected, but then the reality of how things are actually returned to you as the data manager may not be how you envisage them at particular times. So you need to consider the structure of new data, any new data that's coming into the system, and accept that you may not actually be able to fully define what it's going to be until you actually start getting that data flowing in. And the third thing, important thing, is data standards, which are basically agreed ways of doing things. So, we'll talk about data standards in a minute. Okay, so first of all, data types. So the most important thing, unsurprisingly, is use the correct, or at least a correct, data type. Now, there may well be an obvious optimum data type to use, or it may not be immediately obvious but there may be a number of choices which you have to make a choice. So a simple thing, you've got a number field. So in your entity relationship diagram, you've got a field, an attribute that's going to be a number of some kind. Remember, in the entity attribute diagram, you don't declare whether it's a number or anything like that. It's just the name of a field. In the physical model, you have to actually implement a data type. So you've got a choice here in Postgres of all these different data types. Now, which one do you choose for any particular job? Well, you have to consider what the range of values you're likely to experience, what range of values you've got in your present data set, the range of possible future values that may happen, and how that value is stored or is in various data standards, how various data standards say that you should store that value. Okay. So we've got a choice of data types. So, not surprisingly, you choose the data type that encompasses the required range, but minimizes the disk storage. Okay, so if we go back up, we can see that a small int only takes 2 bytes on disk, whereas if we're doing a double precision, we're storing at least 4 times as much disk space is being used for exactly the same number. So if we're stealing an integer that never goes beyond this range, as a decimal, we've used 4 times more disk space than we should have needed to. Everything's going to be slower. Database is going to be larger. And this, you know, in small databases, this often makes very little difference. But when you're saying a database that's maybe a gigabyte size, suddenly you've got a 4 gigabyte database instead of a 1 gigabyte database, and that makes a real difference in speed of response, usability. So it does make a big effect. And then think about it. So if there are no negative values, then there are options like doing things like using assigned numeric type. So you can change these standard numeric types to only do positive values, for example, so that you can get twice the range by basically saying we're not storing any negative values in. So there's all sorts of tricks like that. If you've got something, a figure to 2 decimal places, and it only ever goes up to, say, a value of 100 or 1,000 or something like that, you can get away with not, instead of storing it in a decimal with 2 decimal places, store it as an integer, and then whenever you want to get the actual value in the metadata, you say this, you multiply this by something like by 100, or divide it by 100. Okay, so if we've got a figure something like 20.12, and we know it never goes over 100, rather than store it as a decimal, multiply all the values by 100 and store 212 as an integer in a small integer field using 2 bytes rather than using 8 bytes in a decimal. Again, huge 4 times increase in efficiency. So think about this. Now, whether you want to do this or not, if you're shifting huge amounts of data, it's a good idea. But if it's just your database on your little laptop and it's got a few hundred columns, it's probably not worth doing. So these things, as I say, it depends on the circumstances. Time. We're going to have a whole lecture on time. It's one of my favorites. And really very strongly, I know it's awkward. I know their date types are, personally, I find them quite hard to deal with. But please do use the correct relational database data type. Don't store them as characters or numbers, because you can't do date calculations on them. Or if you it's not that you can't, but it's a lot more difficult and you have to implement that all yourself. Much better to actually convert them into a data type and then use the time functions upon them. And that's really important because time data types are not something that people are used to using, and they're not, unless they're particularly used in an application, developers don't see a reason why they can't just slap them in as a text field or a number field. You know, you could have year, month, 1 to 12, day, 1 to 31 in different fields, time, 24-hour clock. That's not a good idea because then you have to take all those data out, those different fields, turn them into a date time thing before you can actually do things like calculate how many days there are between 2 records or things like that. Think leap years and things like that. It makes it difficult to calculate them, especially if you're calculating time in different time zones around the world and other exciting things like that. So do make that effort to put them into time functions or time data types. The only type that I think you can get away with it, with not using date times, is where you just have a year. And in that case, I think you can get away with an integer absolutely no trouble. I use integers for years all the time. So you can get away, if it's just a year, you can get away with it. But and if it's just a month, you can probably get away with it as well. But it builds up. If you're getting days, then that becomes difficult because there's different numbers of days per month, different number of leap years, not leap years, etc., etc. So, data standards. Agreed, standardized schema. I'm going to use the schema. The word schema is generally means database design, okay? Schema is a design for storing data related to a particular domain. So it's an agreed set of standards. They are defined by many, many organizations for different reasons. So the W3C or WC3, I can never remember whether it's W3C or W3C, I think it's W3C, defines standards for the World Wide Web. The OGC, I can never remember, Open Geographical Consortium, define standards for spatial internet-based mapping, basically, and we'll see lots of that in teaching block 2. Various groups define things like, so the GBIF group, the Global Biodiversity Information Facility, which is a global database of species distribution records and museum specimens. They define standards for biological biodiversity records across the globe, for museum records and for observations of species. If you go out and see a bird or something on a tree and want to record it, they define standards for that kind of thing. There are so many standards. Building information management standards. Who defines those? I've no idea, but it's probably a bunch of surveyors and engineers and people like that gathering around a table. So lots and lots of these different standards. Sometimes they're linked to things like accreditation. So an organisation, if you want to get your site accredited, then it maybe needs to meet standards defined by various organisations. Accreditation is not something that's big in software, not that I'm aware of, but I suspect it will come. But certainly if you're doing things like mission critical software for perhaps, I don't know, the military or things like nuclear power stations or things like that, accreditation may well be a lot more relevant, so bear that in mind. And the data standards exist for both data and metadata. Okay, so they exist for both things, data and metadata. So, for example, a data standard would be the Royal Mail Postal Address File Standard. A metadata standard example is the European Community INSPIRE system, which is called the Infrastructure for Spatial Information in the European Community, and it provides, what this is a metadata standard for spatial data sets collected across the European Union. So it's one standard across the Union for European Union level collation of information. So here is the postal address file. So so I think we've raised this, I can't remember who, I was just talking to one of you about this, or maybe it was in the lecture, I can't remember. The question is, what is an address in Britain? What is an address in general, and what is an address in Britain? Well, officially in the UK, or as official as you can get it, an address in the UK is a place where the Royal Mail delivers post to. It's a postal address. And that's about as good a database, standard database of addresses in the UK as exists. Now, there are maybe other places that you could call an address. You know, the barn up the hill behind the house, this house. But it doesn't have a post. Post isn't delivered there, so it won't exist in the... It won't be an address as far as the post office is concerned. So the post office maintains something called the Postal Address File, PAF. PAF is their list of addresses where they deliver mail to in the UK. This is the format defined for the postal address file. So the post office says that their postal address file has an organisation, department name, PO box, and these are the various fields in the postal address file. Just tells you what doesn't. It's not telling you. It's a kind of logical model, or sort of halfway between a logical. It's a logical model. It's just telling you what type of data is. It's all text fields, and how many characters, and that's it. Now, how you implemented that in a particular database, whether you're using a varchar or a limited car or character field, that's a design decision in the physical design. But these are what the post office used to define addresses. And because the post office use it, and we mostly want addresses because we want to deliver things to addresses, many, many organisations, unsurprisingly, use the postal address file and have a copy of it. The Royal Mail basically sells it. It used to be that it cost a ridiculous amount of money 20 odd years ago. I'm sure it's vastly cheaper now. But you can basically, so when you go online and say enter your postcode, and if you're ordering something on some kind of shop, online shop, you enter your postcode, and then what it does is they've got a copy of the postal address file. They go and search for the postcode, return all the building numbers that go with the postcode, and you get to choose what house number you have within the postcode. So the postal address file is everywhere in the UK. Just about every big organisation, council, company, private company that uses addresses, I suspect uses the postal address file, almost certainly. Now, if you're collecting address information for your own project, should you use the postal address file format or not? That's a design decision that you will need to make, and I'll come back to that, I think, in a minute. Just have a few little looks at this. Not only is there that simple table that tells you what names of the fields are and how big they are and what data type there is. Also, going along with this is a description that defines what the fields are and what the table actually contains. And for the assignment, this is really important that you provide these kinds of definitions for the entities or the tables that you produce, the entities that you design in your assignment. So it tells us exactly what a locality is, a geographical area. It defines what a locality is. It defines us what a postcode is. Tells you roughly some information on a postcode, only one locality per postcode, all addresses in postcodes. So there's a one-to-one relationship between locality and postcode by the sound of it. So you look at these definitions. So it's not just the table, it's the definitions that go with it. And these should be as unambiguous as it's all possible. To implement or not to implement a data standard, that is the question that we are faced. I tried to expand the next line of whatever, has it Hamlet? I can not really big on Shakespeare, but gave up on that. Do you care about data standards or not? Should you care about standards? Well, you should always care, but you shouldn't always implement them. So why would you implement a data standard? Well, what's the purpose of data standards? Well, it's what we call interoperability, which is the ability for systems and data to talk to each other. Basically, if we do things differently, it's difficult to talk to each other, unsurprisingly. If we're all speaking slightly different languages, communication is compromised. So if we all speak the same language, the language in this case of the postal address file, then my addresses, I'm the council, and my addresses, and this is perhaps a private company involved in doing mail drops or something, and they have a database of addresses. Because they're in the same format, we can hopefully bring them together and match the addresses with minimal problems. But if one of us has used a different data format, suddenly we've got to reformat into a common data format to bring the two data sets together. So, standards are about interoperability, the ability to communicate between software systems and to connect data together. Well, it may be that interoperability simply is not a requirement of your system. It's a little standalone database providing information, say, on coffee shops down in Kingston Town Centre. It's never going to be connected with any other database. Who cares? Fair enough. So it may not matter. Your use cases, the reason why you have the database, it's just never going to be linked, or you can't envisage it being linked with other systems. Now, that's not a reason for not using PAF, but it's not a reason for using PAF. The standards may not meet your requirements. So there may be some additional information you want about addresses that isn't embedded in the PAF standard. For example, dangerous dogs live here, be warned, things like that. Crazy occupant, is liable to shoot you, be warned. Some kind of additional information you might require. So the standard might need you. Now, obviously, if you're just expanding the standard, you've just got some additional information, that's great. But if there's a conflict with one of the fields in your standard, then maybe the standard is not something you need to, it's going to be a problem adopting the standard as defined. Now this last one is probably the most important, most important is the most common problem, is that adoption of a standard may result in a bloated design in which not all the standard fields are used. So standards are designed by committees or agreed by committees. I don't know how many of you have spent how many hours, days, years of your lives in meetings with people trying to decide things around talking about trying to define something around a table. I've spent weeks of my life involved in this, and I assure you it is a long, slow process. And what happens is you get all the stakeholders come to the table, and all the stakeholders have all the things that they want to implement. And the danger is that you agree to everything. So somebody wants the PAF, thinks the PAF is a good idea, the PAF standard is a good idea. But the reality is, and it might well be, but the reality is that maybe 3/4 of those fields or half those fields in the PAF file never get used. You never bother entering the data because it's not required for what your application. So you may adopt the standard, but you've ended up with a much larger database because there's all these empty fields which aren't being used. So at that point, you've got a decision, am I going to have a big bloated database which meets the standard in every way, or am I going to not adopt the standard for some reason? So how do you make that choice? Well, this is pretty self-evident, really. First thing is you need to scope out what standards operate in or intersect your problem domain. So, for example, you're geospatial scientists. So there are obviously geospatial standards, but there are also potentially standards in the domain that you work in area. So my last job, I was integrating spatial data with data on biodiversity. So I had standards to consider for spatial data, standards for biodiversity informatics, as it's called, so standards for biological data, standards for genetic data, and I was kind of had to decide which among these various standards were relevant and which ones I could ignore. There's a lot of overlap between standards, not surprisingly. So there's a standard for, as I've mentioned, GBIF, for museum specimens. One of the attributes of a museum specimen is where it was collected. So there's a spatial component. So there's an overlap between the biodiversity standards and the spatial standards. And we'll talk about standards, I'll talk about standards some more. Often standards are designed so that the overlaps match quite well. You take one field from an existing standard, so GBIF for its museum specimen standard may have taken the spatial fields from a spatial data standard and used those. But there's no guarantee that all standards have done that. So there may be some problem in that there's miscompatibility between how geography is stored in one standard and how it's dealt with in another standard. And then there's simply, you've got to sort of look at those standards, look at the domain area, look at what the application is about, look at where the application is going to link with other systems, and just start to consider the costs and the benefits of the extra effort in involving standards, because standards will involve extra effort to initially implement. But once you've implemented them, they may reduce the amount of effort in the future for addition, as I say, bringing data sets together, bringing software systems together. There is no clear-cut answer. Much of the stuff has no clear-cut answer. You have to think about it in the circumstance that you're in. Okay, relationships to tables. I think we'll just try and press on and we'll see. Hopefully it's not too much more to get. Okay, so we've got our entity relationship diagrams and we have to turn them into tables. So here's a few kind of rules of how to do this. So this has got a simple system. We've got passport control, and we're tracking people moving through customs with dodgy passports, basically. So a person here has an identification, has one or more passports. Okay, so passports have a passport number, maybe some kind of information that's on the passport itself. Date of birth, place of birth, things like that. And then we've got people. And people have a pass. So each person has a passport. Actually, that's the one where so passport, but there's a person ID. Sorry, that person ID. Oh, I think that's wrong, shouldn't it? That should be, so a passport has a number, it has a place of birth written on it, and it has a date of birth number. Then you might have an information on a person. You have information on a person, and you know what passport they should have. I think that's what it is. So you know out of your passport list of passports, you know what passport they should have, their legal passport. They also have a name, you know their name, for example. So if we have a situation like that, it's dead simply a one-to-one relationship is just implemented as a foreign key in the person, in the one relationship, and we have a, oh, my brain is right here. So we have a foreign key for passport number. There's our passport number in our person. Yep. So we have, I've had a rotten cold for the last week, so my brain is still a bit fried over. So if we have, so for each person, they have one passport. That's incorrect, isn't it? Place of birth, passport number, that's their official passport. So they have their official passport. That doesn't look right. I'm going to have to think about that. Yeah, hold on. So a person can have more than one passport. But these are not official passports. Okay, these are just... Let's not worry about the reality of the situation. Let's keep it as simple as possible. Let's not bother about all the possibilities. So one person has an official passport, but there are many passports. There are many passports. Okay. So we need to know which. That's a one-to-one, isn't it? That's a one. So the passport number. That's the passport number. So there's many passport numbers. So each person, that should be a... I think that's wrong. I think I'll have to go back to that one. I'm sorry about that. I'm having a problem over that. That's the wrong one. Let me go back to that. Let me reconsider that after the break. Okay. Okay, so in this case, sorry about that. We've got the problem. So in this case, we've got N to M. So we've got one person could be using a whole number of passports, and any passport could be used by lots of different people. Yep. It may not be the reality of the situation, but you can see them. They're pulling off the photo of that passport, sticking a new one on. Somebody else is going through the system. It probably happens out there. I'm no expert on passport fraud, as you could probably gather. So there's a relationship between use. The relationship is use. Each person uses a passport, and each passport is used by a person. And we know what date the passport comes through customs. Okay? Now, this is quite easy. We've got a group of people. We've got a person. The person ID is integer, and they have a name. And then we have a passport number, and a place of birth, and a DOB on the passport. So what we do is we can take this relationship gets turned into a table. And what we need is we need to know which person was using which passport on which days. So from an M to M relationship like this, what we end up is 3 tables. Remember I was saying earlier that there's a mapping here between entities onto tables. Well, in this case, the relationship is turned into a table as well. Okay. Now, slightly more complicated here. If the use of a passport is dependent on both the person and the passport, then if we have to have person and passport, so whenever something gets entered into the database, we need to know about both the person and the passport to enter a record. Okay, so we need to know who this individual was coming through as well as what passport they were using. Then we can implement a composite primary key on this joining table, yep? Because one person is only going to use each passport once. And in fact, it should be on the use time as well, because a person could be using the same passport on multiple occasions. So I should probably have the use date as well as a part of the composite key. However, if this is probably more common, then the use is just dependent on the passport. You know what passport got used, but you don't know who was carrying that passport on any particular day. But you know when the passport was used, and you know somebody came through with a passport on that particular day. So in that case, use is just dependent on the passport, in which case we would implement as a new table with its own primary key and foreign keys going out to person and passport number. A passport number we would have to implement a non-null constraint. Okay, so the take-home message is there's the same relationship in an ER diagram, depending on the circumstances, may result in a slightly different physical design, depending on the constraints that exist between these, how the details of the constraints between the relationships. Let's get back to that first one first, see if I can work, see if my brain has recovered from this one. Okay, so implement is a foreign key in person on passports. One person has 0 or more passports. It should in fact be the other way round. Sorry, this is my mistake, dear me. So passport should have person ID as a foreign key in there. That's the way it should be. Apologise for that. So person ID should be a foreign key in there. Passport number should not be a foreign key in person unless it is the official passport of that person. Yeah, okay, that's better. No wonder there's an error on that. I'll try and correct those slides. Okay. Columns. Should we have a break? Yeah, 10 minutes. So 10 minutes, and then we'll finish off this. There's not much to